So the first step, we need to start a new file. So I think it's already done by the software. When you start, it will open to you a new file. And for this, you can, as we already explained this a few weeks ago, you can enter the proposition as from a list or as a table, like this from here. If you have the data here in Excel sheet, you can just take it by copy paste. Okay. You will find that each PVT report usually has composition as mole fraction or weight fraction. It's recommended that you use weight fraction composition. Why? Because you will, in this case, you will be able to use molecular weight for C7 plus as tuning parameter. We said that C plus component, pseudo component, molecular weight, this value is measured inside lab and has some uncertainty. To use this as a tuning parameter, you will need to enter the component, enter the composition with weight percent. If you enter the composition with weight percent, you will be able to use the molecular weight as a tuning parameter. If you enter the composition as mole percent, you will not be able to use this one as tuning parameter. Today we will not do it like this. We will avoid this, but just maybe you will use it in your term project or last project. So just take this copy mole percent for the composition and put it here. We said it's better to work on weight percent.
We just enter the same table of molar percent.
Because if you want to enter to change, that's a good question. If you want to change this to weight percent, you have to come here and change from molar to weight. Like this. So in this point, you will need to press verify to link the components with the database. So you will find that each component is defined correctly. It understands N2 as N2 and so on. But for this component, which as usual is not defined inside database, no one knows the pseudo component for each fluid. You need to measure that in that. So this is pseudo. You need to enter for this component. You will still need to define the properties for this component. So after this, we press enter composition. So you will find that the software already shows the molecular weight for each component. This is because each component is already defined. Those are pure components. We know exactly what's the molecular weight for nitrogen, for CO2, for C1, and so on. But for the pseudo component, you will need to enter this value. And you can take this from here, it's 218. It's measured inside lab. You can see it here. Those values are measured inside lab. If you open the third page in your PVT report, you will see the composition and the data for the pseudo component, which is specific gravity, ABI, and molecular weight. This is what we are talking about, these values. These are measured inside lab. Now what you still need to enter in the software, you will need to enter the reservoir temperature, reference depth, and reference pressure. And if we go to our report, we will see that original reservoir pressure is 4,100, and this is the reference depth. However, there is a sampling condition here, where they just report the depth, and here they mention the last reservoir pressure. And they said when we extrapolate that pressure to reference depth, they found it 4,010.
Where is the reservoir temperature?
Mm-hmm.
Reservoir temperature.
Yeah, it's 200. You will need to take the reference depth, which is mentioned here. Oh. This one. This is the depth. And you will need to enter this pressure because we prefer to start our PVT modeling always from the highest pressure. And however, when we sampled the fluid, it was above the bubble point, so the composition does not change it. That's why we are able to take this pressure. You know, below the bubble point, the composition changes. But above the bubble point, the composition is constant. So we take the sample at 410, but when we enter this in the software, we will take it for 4,100. There's no difference because the composition is already constant.
We always have to consider the initial reservoir.
Yeah, that's why. Because when we do simulation, we will start from the initial reservoir pressure, not from the sampling pressure. So you can take those data from Okay. You remember when we practice equation of state that we use the molar percent for each component and its properties. We use TC, PC, eccentric factor. And to be able to use the equation of state, you will also need to calculate the pseudo-component properties. The software will do this automatically, and now we just press exit and save, but we will need to go back here to this photo. We need to define the pseudo-component properties. So if we just, yeah, it's appeared already. So it asked you, when we say exit and save, it asked you, no, we cannot go further until you define the properties for the pseudo-component. You gave me already the mole percent and the molecular weight, but what's the other value? And here in this point, you will need to enter the specific gravity. If you remember in PVT course before this one, you use correlations for pseudo-component where you use the molecular weight and specific gravity to define those properties. So there's a correlation, and those correlations are implemented inside the software. So here we will enter the specific gravity. Which is here, and you can find it here. Now, how we use correlations? We just say calc value. You can maybe define which correlation you will or you want to use, but usually we keep this as it is. Just this calc values, and it will calc everything for you. I don't know if. No. Just keep it like. If you want to do that, maybe do it in Term project. Yeah. So those values will appear like this. Now the equation of state is ready because we have the properties for the pure components and the properties for the pseudo component. There is still one problem, but just we will exit and save, but we will go back to this problem. So now this is the first step. Enter the necessary fluid information, but here we need to construct the PVT diagram or phase diagram. To do this, you have to press this button here. However, each bottom here you can access from the bar menu. You can do calculation phase envelope. It's the same. So we said we have the properties for all components, and now the equation of state is able to calculate everything, to calculate the phase envelope and other properties. But what we still miss here, we want to show where is the bubble point pressure or saturation pressure. Is it here? We enter the reservoir temperature, we know it's in this line, but is it above or below? To show that point, you will need to enter it from, this bottom here. Set test Can anyone? Yeah, how you know the saturation pressure?
I know the situation.
Yeah, how you know from the report, not from the Excel sheet? How you know? CCE, yeah, exactly. So in CCE experiment, what we do, we measure volume with pressure, but we at certain point we note that the volume change uh, is big. Then we know there's a gas coming out from that liquid. So that point would be our saturation pressure. I can draw it here. So at the beginning we measure just volume, and we found that the volume decrease like this, then there's a huge decrease or increase, sorry. So at this point you will define the volume at saturation pressure, and this is saturation pressure.
1040 psi, I guess.
Yeah, 2620. And then we convert this data to relative volume. We take this value and we take each value here, we divide it by V at bubble point, and then we have a table for V relative volume. This is exactly what we have here. And of course, it will be 1 here in this point because we define the volume to itself. So from CCE, we can know the saturation pressure. So in the software, we need to enter that here and press OK. You will find that this point is here. I just can. No, just Psat. This is Psat for saturation pressure. Just as the temperature and the. Pay attention to the units. Usually you got PVT report with PSI, not PSIG. So before, in this case, it's easy because we have the pressure is already in PCI gauge, but for 10 projects you might have something else. How? Yeah, 2,600. Yeah. We said that we need to show the bubble point pressure here in this envelope. And how we know the bubble point pressure? We go to the CCE, and when the relative volume is equal to 1, that's the bubble point pressure. So there's a hint after the first step which says that the composition can either enter as mole percent or weight percent. However, it's recommended to enter the composition as weight percent, and in that case you will be able to use the molecular weight for the pseudo-component as a tuning parameter. It is written here, you don't need to write it out. It's written. So we go to the step B. Oh, before we go to the step B, we agreed from the beginning that we said we should save. Now we are still here in the same step, but we should save before we match saturation pressure and so on. We should save each step before we go further. So how to do it? First of all, you have here you will have the PVT model. It's called stream as fluid. So you will have different stream. For example, if we copy this and put it here, you will have well stream number 2 and so on. But we prefer to change the name for this one to indicate or to help you to differentiate between the streams or the fluids. So let's say we want to change the name for this one. You need to come to this button here, and you can change the name from here. It's preferred to name this fluid by the component numbers and the data which you have matched. So we have, if you count these numbers, it's just 12 components. So we can say just 12 comp and without anything else because we have not matched the Psat or density. So you see here, why we define component, because maybe we use lumping or splitting.
Why did you write 12 components? Because there are 12 components?
Yeah, there are 12. And I'm answering this now. Yes. We have a simple composition with the 12 components. What we will need, we will just define that this fluid is 12 components to indicate to me that in this case I take the composition as it is and I did not match anything. If I match Psat, I will say 12 component Psat. And if I match density, I will write 12 component Psat density. This naming the files will help you just to understand which stream for which case or for. That's it. So now in the second step, we will need to match the equation of state oil density at standard condition with standing Katz correlation by tuning pseudo-component properties using auto-match. So before we match the density, we will need to copy this one because we don't want to change everything in the same fluid, but we will copy it here and we will add the note about this oil density. How you copy this? You can come to this one, plus mark bottom, and copy existing stream. And here it says that it's named like this, but you need to remove 2 and say density, oil density. It's like this. What?
The first one is saved or not? We did the first one.
The first one
Is saved or not?
it's safe. It's safe. Okay. So here we just write all, then, or just you can maybe oil density, OD, just to the most important thing that you understand this. You can name it whatever you like, but you should understand which fluid it is. So we say copy stream, and then we will have this component. Here we will try to match the oil density at standard condition. So before we go and match the oil density, if we show the phase behavior again for the two, you can just select the two fluids. They are the same fluid but at different steps. You will show them at the same envelope. You will find they are identical. It means they are still the same. We did not change anything. However, if you want to know the properties or how the equation of state calculate the properties, you will need to go to this bottom, and here you can find the values which are used and the results. In this bottom, we will be able to find or to see the flat oil properties. And here we can calculate some values such as phase envelope saturation pressure. If we go here, we will find that the oil gravity initially is 23. And here maybe you see the gas oil ratio and condensate gas ratio. And here you will be able to calculate or to show the phase envelope for each fluid model you have, and you can also show the saturation pressure at reference condition. So if we want to calculate the saturation pressure, we just choose this and press calc. So this is the saturation pressure. It's lower than the lab data. In lab data we have 2,600, and here it's 2,300. And you can find that here. This is from lab, and this is from equation of state at this point. So now we will do this step where we will try to match oil density. To do this, we have to go here. This is the window which appeared after we entered the composition. This one is called inter-component data. You can reach that from from this one. It's the same. If you go to data, and composition editor. Oh no. Yeah. Enter composition. Yeah, that one. We will try it again from here. This one, it's the same. So now we will how we can match the surface density, and with what we match that. We have a correlation which is called standing and cats. And that correlation is considered as a reference for you for oil density at surface. So, so at surface condition, you will try to match the equation of state results with standing and cats correlation. How you do that? Just you came to pseudo-component properties, and as we said, to match the surface density for oil, we will use the pseudo-component properties. Why we use a pseudo-component, not pure component? Can anyone answer this? Yeah, exactly.
What?
Yeah. Why we now we want to? We know that standing at CAT's correlation is my reference, and I need to make the equation of state results match it with with these values from standing at CATs. To change the equation of state results, we need tuning parameters. For tuning parameters, we said we should use pseudo-component properties. Why we use pseudo-component properties, not the pure component properties? Because here we have the highest uncertainty. We don't know exactly which the critical volume and which the right eccentric factor.
Then we can change.
But we will change them until we got the match. So to do that, we use this button, auto match. But just pay attention before you do it. Before you do that, just came here and see the gravity, so oil gravity. Now it's 23. Now we will try to match. And we will see how that value will be affected. We will go back again for that value. It's 23 now. Just remember 23. We do auto match, and just see here the values will change, and the color is changed. It's like there is a warning that the values were not correct, or you have uncertainty, or you can change them to have better match. So when we press auto match, we just have to store the pseudo component, the current properties by this button. We press store and we check this one, use original pseudo props from store. We store this data by this button, and we check this one to use the data which you stored. So store, press yes, and use original pseudo props from store. Exit and save. Oh. Okay, auto match, store, yes. Is it right? Okay. Yeah. Now we will go back and see how the API is affected. We press. When I want to know anything related to our fluid properties, we came to this button. We need to use this button many times to see how my properties change. So just came here, black oil, and you will find that your oil gravity API is 38. It was 23 and now it's 38. If you compare this with DLE data, DLE differential vaporization data, I will show it here. If you compare the API now, it's near to this value, which is measured inside the gravity of residual oil. It means at the last step or at saturation condition, it's 35. So now 38, 35, they are near to each other. This is just indication. It should not be exactly a 35. because we don't match API with this value. We match the equation of state with standing correlation. Last step, yeah. Yeah? You got? Which, how much is enough? I will repeat the last step. We said that you will use the pseudo-components properties to match the oil density with from equation of state with standing correlation. How you do that? Just press this button here. This one here, which is for intercomponent data, and go to pseudo properties. And here, you need just to do 3 steps. Calc values, or 4 steps. Calc values, auto match, store, check this one, and exit and save. Okay. You will find that when we match the oil density, the phase envelope changes a little bit. So actually, I am recording a video. I will give it to you. Okay. So we have to what?
Yeah, we have to continue.
Yeah.
Okay.
There's no time. You have 1 hour. Okay. So now the third step, where we need to match the reported bubble point. So what we need to do here, we need to make this envelope exactly at this point here. Yes. So now we will need to save this one and copy it, or copy it again with a new name. So just copy existing stream plus copy existing stream and we name it PS. So here we match oil density, and now we will match saturation pressure. Okay. Copy stream, and we will try. Pay attention that when I move to these ones, I choose the fluid before I press anything here. So when I am talking about this one, where I have matched the oil density, I press this one to show the phase envelope for this fluid. So it will be shown. However, if I want to add another one, I can press it from here and press calc. They are exactly identical because we did not change anything. So how we match the saturation pressure? We have 2 ways. Either we match the saturation pressure by auto regression or auto tuning, or by manual tuning. What's tuning? Tuning where you change the properties to match certain lab measurement. we have observation data and we have calculated data. Calculated data is from equation of state, and observation data from lab measurements. So this is, so usually let's say you have any property here with pressure and you have points like this. When we show just points, it means those are observation data. When we want to show the calc values, we do it like a line, something like this. So calc values, it means with equation of state, and this is also used in simulation. When you have to do a history match with data recorded for your well, you show that as pointers, and you will try to make your simulation model identical with these points. So now what we will do, we will try to match just one point, not many points like this. We will try to match this point. This is observation data. We show it like a point. We say that here. And we will try to match this one with this one. To do that, we use something called tuning or regression, which is the same as history matching for reservoir simulation. In tuning, you have two ways. Either you do it manually or auto-tuning or auto-regression. How you do it manually? You go just here and try to change the properties here. And this is more difficult than auto-tuning because you will follow these numbers and you try to think about them. Yeah. And for auto-regression, you press this button here. Now we will not use it, but in further projects, I think the next one we will need it. We will not use auto-regression now. We will just use manual regression. For Psat, you can match the saturation pressure either by binary interactive coefficient or critical properties. But it depends on your fluid, and maybe you can try this and investigate this by yourself. But in this lecture, we will use just binary interactive coefficient to match the Psat. However, you can match the Psat with the critical properties for the pseudo-component. Is that clear? Who said no? Okay. So now to it says also here, it says that for matching, you may also consider splitting the heaviest components into several fractions. You will take that in chapter 6. This chapter, heptane plus characterization, where what they do, they take the heptane as the pseudo component, this one, and they separate it to 4 components or 3, depends in your case, to be able to use the properties for these components to match your data, to improve your data. So now, let's copy this one again, and name it 14 component, where we will split the last pseudo component to 2 pseudo components. This is just to help you to compare what's the difference and which one is better. We didn't change, yeah. Now just came here. Yeah. So now we will split the last component to 3 components, or 2, depends on your decision. There's no fixed number. The idea is just to split the pseudo component to certain numbers, and you will use several pseudo components to have better match instead of just having one pseudo component. Is that clear or still? Because sometimes if you edit the properties for one pseudo component, maybe it's hard for you to match the lab results because you have, for example, just 4 tuning parameters. But if I split this to 3 components, I will have 4 tuning parameters multiplied 3 components, then I will have 12 tuning parameters. This will help you to improve the results. So now let's say that we will split the pseudo component, the last pseudo component, to 3 components. So our composition will be now 14. Just minus 1, it will be 11. The 1 we will split it to 3. Then 3 plus 11, 14. Do I need to explain this? Yeah. So how I can split, this is still, if you count those, this is still a 12 composition, 12 component composition. How I can split this to other 3 components? Just come back here to pseudo props again. And here you will find that there is split or profile and advanced. This is called advanced PVT, and you will take it at the end of this course, but just try it to have idea about it. If we press this point here, you will define which method you will use for splitting. There is Whitson method, which is the most famous one, and here you can define how you will calculate the molecular weight for each component. So you can also choose Whitson here. And remember this factor here, alpha factor, it's used just to describe how you will split these components. For example, if we talk about the molecular weight, if we do the molecular weight with mole percent, I will find something like this for my components C1, C2, and this is C7 plus. And now we are talking about how we should split this to heavier components. Then we are talking about describing this like this, or like this, or like this. This is defined by alpha factor. So here we can choose the number of pseudo components that we want to have. We will ignore this one, or we will split this one to other 3 pseudo components. So I chose 3, then set even split. So you will find that by this method I split the pseudo component into 3 components. And pay attention, we are doing splitting for this one, 14 composite, 14 component. Don't do it for this one.
Yeah, but ours is C7, C10, not C9.
This is done automatically by the software. It uses the Wilson method to split this value. So, yeah, it shows from 7 to 9, and from 10 to 12, and 13 to 12.
Our correlation choose from 7 to 10.
Yeah.
Ah,
The same.
you are different. Have you choose Wilson here and one?
You know, our maximum
Okay, no
is
problem.
22, your maximum is 22, ours is 23.
No problem. That's no problem. No. And exit and save. Before we do auto match again for those components, we just need to see the properties, how they are changing. If we go to API, we'll see that it is increased to 41. However, we try to do auto match and we will see how this value can be affected. So, auto match, store, exit and save. So if we go back here, we saw that this value, again, 38. So we improve the oil density and we keep it improved. Yeah. From which point? From splitting? Auto match? Yeah. We said that for this fluid, we will press this bottom and pseudo probes. And we press advanced here to split the C7 plus component to 3 other pseudo components. We do that here by choosing 3, and maybe you will need to choose Wilson here, and just set even split exit and save. After that, you will see that you will have 3 pseudo components. So, press auto match, store, use original pseudo probes, and exit and save. So now we have oil density matched for those 2 fluids, and we found that when we split the fluid, we will got different phase envelope. Now we will try to match the saturation pressure for this one and for this one. Here you will need to read this hint after step C. And it says that you should use binary interactive coefficients in a small range. It's around 0, not 0.3 for example. It's just 0.1 in maximum. So start from 0. Start from 001 and try to not exceed this value. Why? Because binary interactive coefficients, they are sensitive, and we say also here use binary interactive coefficients as fitting parameter. Why we say that? At the beginning we agreed that equation of state is an equation and it was built using physical concepts. And we should not take the equation of state parameters as mathematical approach. where we can change everything as we want. However, binary interactive coefficients are considered as tuning parameters. We can deal with them as just numbers, and we don't need to care very much about the values. However, we just care about the range. We should not exceed, we should not use, for example, binary interactive coefficient 1. That's large. And we should not use 0.3. Also, it's large. Try to stay below or around 0, below 0.1. So if to do that, you just go here. We say now we will do manual tuning. So to show the properties or change them, you came to this point. And here you will see the table for the binary interactive coefficient for your composition. Now we will do it firstly for 12 component system. And binary interactive coefficient is usually changed between C1 and the heaviest component. If you have maybe some questions about this, you can read this reference here, or this reference. I referred to them 2 pages, and from there you can get the knowledge why we use pseudo-component binary interactive coefficient between C1 and pseudo-component. However, there is in Whitson box they said you can use it between all of them, but it's preferred to use few of them, or at least one of them. So it's better, the best approach that you can do, change the binary interactive coefficient between C1 and the heaviest component. So we are talking about this value here. So now, if I just do 0.01, let's say 0.05, and we want to calculate the saturation pressure. We press quick calc, saturation pressure and calc. We note that our saturation pressure improved. It was 2,300 and now 2,500. So we will keep increasing the binary interactive coefficient until we make it 2,620. So each one should try it different values until he can get the match. Okay, so I could got this value 2,620 with with this value. So you can see that I did not exceed 0.1. However, if you tried this with your fluid and you found that you exceed, for example, you got the match with 0.3, then avoid using that. Try to split your pseudo component to 3 components where you will use lower values. So now even if we show the phase envelope, we will see that we match this point. It was below and we match it now. But is that enough? Is that means that our model is accurate? No, because we match only one point and we don't know the other properties for this flow until we use the lab data.
Can you plot what we have the splitting of
Yeah. This is here. 12 component, we match oil density but without matching saturation pressure. And here we match saturation pressure. You can see that it was here and now we match that. Hmm? No, no match. Okay. Okay. Now we will try to do the same thing with this composition, 4 component, where we will have 3 pseudo components. We will have 3 pseudo components, so we will change this number, this one, and this one. And maybe you have the choices either to change the heaviest pseudo component with C1, or you change all of them. And if you are going to use all of them, try to use the same values, or it's not necessary to be exactly the same, but try to keep them near to each other. I used just 0.05 and I got this value I still need to improve that. Yeah, now I got the match with those values. You can see here with those 3 values. The same? Not the same. So now we will go to the next step. We can show the phase envelope. You see that I got the match with 2 fluid systems at the same point, but they space envelope. So now we will go to the next step, which is step D. Match the reported density or specific volume at saturation pressure using the same equation of state model. So now maybe we use one of them or both of them. I will use this one. I will keep working on this one because I have more ability to use more tuning parameters to match the equation of state. So you can either start work with both of them or one of them. It's your choice. So I will take this one and I will see. So here we will match the oil density at saturation pressure. Before we matched the oil density at standard condition. You know the difference, one at standard condition and one at saturation pressure. So this is what I'm going to use. So now to match, which value should I use here? In PVT report, they give you the specific volume, which is reversed for this, and you will need to 1 divided by this number to have the value for density, and then we will enter that. So let's say that 0, 1 divided. So this is the value for our density, LB per feet, pound per feet, cubic feet, 40.967. How I can enter lab results? I will need to go to this mark, which means lab experiment results, or as it says here, enter lab data for matching. So here we are talking about properties at saturation pressure. You can enter temperature, saturation pressure, and density at saturation pressure. How much you will enter it? What? Yeah, this is the problem. It happened last year with several students. If you do it like this, then you will destroy your equation of state model. You will try to match this value with kilogram meter cubic meter, and you actually enter the value with pound per cubic feet. So make sure that you enter the value with the right unit. How we can change this unit? Just go to this one here. You can go to that from option units or from this button, and you will find that you have density, and you can use either for input and output. You can change also. Let's keep it as it is for output. We don't need to change, but for input, we will make it LB per cubic feet. You need to press just okay. You see here it's pound per cubic feet and just enter 40.967. Here we will go, we will, one more. We will match this value with the auto regression. For density, we fix density values with what? Do you remember? With Professor Gans. We have a problem with equation of state. When we show pressure, volume, the equation of state is able to predict the values here, and in liquid part it will not work very good. So for that we will have some percent of error, and we call this volume shift. So it means when I calculate, we need to fix this value with volume shift. So that's why when we match this one here, we will need to say to the software, use volume shift to match oil density. However, when we use auto regression, we have to give a weight for each property we are going to match. What does that mean? It's not as tuning as manual tuning. At manual tuning, I change parameters values to get the match. But when I use auto regression, the software will try to match several properties, and when I give different weights, it means focus on saturation pressure more than density and so on. If they are the same weight, it means the software will try to match them together with the same percentage. But if I give different weight, it means that I have to get the match with saturation pressure more than with oil density. So it's recommended to give the medium weighting factor for density. This one should be fixed. Should be 20, not 10. Yeah. This number here. Yeah. This number. What they recommended in PVT box, they said for B saturation, you give 40. Weighting factor, you give 40. For density, you give 20. For volume, you give 10. And maybe you have to have a look for these weighting factors. However, in the software, they are not described like this. They are described from 10 to 1. So this is highest, this is the highest value, and this is the lowest. So maybe you use 10 to refer to 40, it's something like this. You give the highest weight to Psat. So you get one. How I specify weights for each lab measurement? I just press this one here, and I choose the weight from here and set weighting. So it's already high. The software will give all properties the same way. This is the default. But for you, you will need to change. For density, we say it's 20. It can refer to 5 in this case because the software should be from 40 as PVT textbook. But they change it. They make a number just from 10 to 1. So for 20, you can see it is in the middle. We can refer to that as 5 here. So we keep that here for saturation pressure. For this one, I choose 5 and set weighting. I will find that its color is changed to blue. Once you change the weight to a value different than 10, you will have a blue color. So you need to press OK. We already use manual tuning to match saturation pressure. Now we are going to use auto regression, but it's preferred before you use this one to copy it, or I think it's already here. If this one is the same as this, then we don't need to copy it again. Which the weight, it will not affect the weight. So if we draw both of them, they are the same. So we will use this one to match. If we have a problem, then we can delete it and copy this one again. So to do auto regression, we will need to go to this one here. This window will show to you all lab measurements. You will see all lab measurements here. And you will see which you will be able to choose which lab measurement you are going to match. And here you can choose which parameters that you are going to use to have the match. So pay attention, please. Maybe the weighting factor which you have chosen in lab data, you will not be able to see it here. So here you have to edit that again. For example, density at saturation pressure. You need to do a meter. However, you can go back to lab data from here. So here we already have medium, but we will need to edit that again here. So we will not be able to go to regress or regression until we choose the properties that we are going to match. The first step we will try to match just the saturation density, and we will see does that affect the saturation pressure. If it affects the saturation pressure, then we will delete this one. We will repeat again and try to match both of them at the same time. This is just to see is or does the volume shift affect the to match affect the saturation pressure or not. So just choose this one, and here you will see that which properties are you going to use. Normally, for this one, the software will give you the ability to use everything, but you should not do everything. You should just change the TCPC for pseudo-component, not all component. So it's not. If I'm going to do this software, I will not do this choice because some people will not differentiate. which properties should they use for matching. Or at least I will not give this choice as default to prevent people from using the wrong properties to have the match. So this one also in PVT textbooks they talk always about individual omega A and omega B. They are talking about changing the omega A and omega B for each component, not for the all component. So it's preferred to not to use this one. If we just choose this one and press regress. So now I can check the parameter that I'm going to use for matching, and also if I'm going to try to keep the saturation pressure matched, I can check final interactive coefficient. But now I will try just to match the density and saturation pressure with volume shift. So now, if you see here, this is we have two shifts, factors, shift for temperature and shift for volume. This is what we are going to use. So you will find that you are not able to use this one. You can activate it from here. But when we activate this, we will find that the results may change. This is without doing the match. It's recommended. Also, this is maybe will help you in your term project. It's recommended to choose the volume shift at the first volume shift at the first step. How you do it? Just when if I exit from here, option, here you will able, or from this button, option, or from this button, you will be able to use your equation of state, and you will be able to use whether are you going to use volume shift or not. To use volume shift, because what volume shift will do for you will improve the results, because you will do this correction, and there's the default values which will correct your values. But if we say yes, we have a problem. We matched the density, oil density at standard condition, and the saturation pressure. And maybe if we say yes, it will change the result. I will try it and see. So the saturation pressure does not affect it. But the API gravity is affected. And that means that you will need to go again to pseudo properties and to do auto match. You remember we do auto match to improve the oil density at standard condition. So we need to go back again to do it. We do it from here, props. Auto match, store, yes, exit and save. If we go back here, we will find that our API improved better than before. It was 38 and now it's 36, and in lab we have 35. So we are almost there. We improved our results. So it's better to choose the volume shift. I do this just to make it clear for you. If I do it from the beginning, maybe you will miss that point. But you will see now when we come back to this point and fix the equation of state by volume shift, we improve our results. However, even in tuning, you will not be able to use the volume shift to match the density at saturation pressure without choosing the volume shift. For example, when we say when this was no, I could not choose the volume shift in autoregression. That's why I said we have to say yes. So now, if we go to autoregression, you will say that you are able now to use the shift. It was like this before. Now because we have this one yes, but we didn't choose this yes without fixing the density at standard condition. Some people maybe think that they will deal with the equation of state just as a mathematical approach. This is the physics that we should take care about. We should fix density and use volume shift. Sometimes you see that people use, for example, eccentric factor to fix density. And that can destroy your equation of state. Because if we say we have 2-parameter equation of state or 3-parameter. For the 3-parameter, we use volume shift. For 2-parameter, the equation is correct, but it will mislead you here. So it means if you don't use just the volume shift, it means that you will fit this one here, and you will have something wrong with gas. And the equation of state is accurate here. Why you change this part here? Why you match this point and destroy the other part? So what you have to do, use the volume shift to match this point, and this will fix your equation of state. So now we will choose volume shift for pseudo-component to match the oil density at saturation pressure. Here, the weight is not important or does not affect my results because we have just one property. The weight will not affect. But if we have, for example, more than one, and we give high here and medium here, the software will try to match this, then will try to match this. It will make or will pay more attention for this factor. This is the idea of having weights. So now we choose those three and press regression. The first thing we should see is saturation pressure. You will find that your saturation pressure is affected. Changes. So that means you cannot match the density at saturation pressure without keeping the saturation pressure matched. So that means you need to ignore these. You need to go here and choose also this one. I will keep it with high and this one with medium and try again. So regress. No. To keep the saturation pressure matched, what should we choose from here? So the components, yeah, which property? We use what before? What we have used before to match the saturation pressure? Yeah, which property? Is it critical temperature or binary interactive coefficient. This is what we have used. So that is not included here, but you can use it from here. Binary interactive coefficient. We will check this one, and we have several choices. Are we going to use the same number for each pseudo component or individual values? Or just last pseudo component only? So it's preferred to use this one, all pseudo to same value, or this one, it does not matter. I will choose the first one, and you will find that they choose just the last pseudo component. And you will find that the software already gives you this choice with just the lightest component, C1. So now we do regress. We have a look here to see do we have acceptable values in the range, or we have strange values. So it's okay. We're still below 0.1. And if we show, we found that the software gives the value matches. And you can compare the results using this tab. You will see the equation of state result and the lab result to compare between them. You see here, this is your target, this is your lab result, and this is the best result that you can get from equation of state. So we got accurate match here. However, we got accurate match here also. So we could match saturation pressure as this. If you use the wrong parameters to match these values, you will just destroy your equation of state. For example, I matched the density using critical properties. We should not do that. This is just for, as you know, there's iteration for errors, and they calculate the error person, and after 10 times they will take the value with the lowest error value, which is the best value you could have. And we found that it's acceptable, it's identical. We just have this one done. So this is auto regression. Auto regression is easier than manual regression. If you are going to use manual regression to match density, then you maybe need 1 hour just to, you will need to change each parameter by yourself. So now we press OK, and we go back here. And we can compare first envelope between those two. No, no, you don't. They should not be the same because you change it. Make sure that you save it, the regression after you finish. Maybe you still have not changed anything. Yeah. exactly match it. For you don't have to focus a lot for the API and surface because you are matching now lab measurement. So once you enter lab measurement, you want to match that measurement, and then we don't worry because in further steps we will calculate the error percent, and we will know which experiment should be fixed. So at the last step here, it says that generate a written report about your work, recommending the results. And this is just optional. Last year, it was obligated for each student to write a report. But this year, we say just we need the final report to make it easier for students. And if you are going to write a report, it's better for you to help you to write the final report, because you will at the end you will use the same report but with different data.
Okay, can you give us an example of the report? How you have to write it?
I will see that. We will see that. Yeah. I have to discuss this with Professor Gans. Yeah. Everything which will be in the project, you will have like this paper, and you will have a data, and you have a guideline to follow.
Yeah, okay, but for the writing the report, for example, we have to open up the kind of Word file, then we have to do some sort of a snapshot and say.
Yeah, it's all written in your guideline. You just we will ask you to have to show snapshots and so on. Just to you will explain about them, and you will need to know which procedure should I do. For example, maybe I found a students who match density with other parameters. Then maybe this is not good for them. You should always use volume shift for density. Uh, Unfortunately, we don't have the time to work with this project. Maybe we do it next week. Yeah. So that's it for today. Any questions? Yeah, the last step, you need to save this. Please keep this file because you will need it in next set projects. You will need it in CCE Project, because we will add the lab data with this on this file, and we will go further here. So to save that file, save as. And you can name it Psat Project. Last point I want to mention here, you have the choice to enter all lab data at the first step. So at the first step, you are recommended to do two things. At the first step, check the units and check if you will need to choose the volume shift. So let's say that you use volume shift and you check units and your equation of state. We usually take Bing Robinson, we don't change the equation of state. And the second step, it's recommended to enter your lab data. That means you just came here and spend time with just entering lab data. You enter saturation data, saturation pressure data, CCE, differential liberation data, and separator data. And during this step, don't forget to give weights. Or not percent, just give weights. Here we have to give weight for each property. Is it high? Is it low? Is it medium? Is it low? So in your term project, it's better to enter the lab data at your second step before doing anything, before trying to match, before anything. That will help you when you are going to copy those. So when you have a problem, you don't need to enter lab data again at each step. So enter everything here at the first fluid model. Then you will try to match Psat here in this step and CCE, DLE, and so on. This is just to save your time. Is there any question? Plus one.
No, the equation of state actually.
Okay. When I start a new file, close all. This is a new file. So we have our fluid here. We can name it. Before we name it, we need to enter the composition. And for that step, we need just to go option, use equation of state, and volume shift. Or from here, PVT. So we say yes, and okay. This is the first step. And then the second step, we enter the composition. Let's say we choose anything from here. Oh. So now, when I enter the composition, I can check the units, and I should go to this one in the beginning, in the first step. So I enter the lab results here, and I give weights to each property. Also for CCE, I enter lab measurement, and I give weights and differential and separator test. And then I press OK. Then I just copy this fluid and I go to several steps. And for next week, we will, or maybe after, I don't know exactly if there's, if we will have a lecture next week, but we will work on CCE. Is there any questions? So that's it for today.